Very good, Dustin. Okay, so this is basically the spherical coordinates here. And then the second one is cylindrical. Okay, cylindrical. So for cylindrical, this is when we're talking about it's a cylinder centered around the origin. Okay. And in this particular case, your n hat is 1 over a x, y. Okay. And x is a cosine theta, and y is a sine theta. Oops. Okay, and z is z. Okay, yeah, and dA is d what? dz d theta. Okay, dz d theta. So in this case, your r is a constant, which is the a. So it's a cylinder, okay, with the radius of a at here, okay, and centered, okay, centered around this origin there. Okay, that's what we call a cylindrical kind of surface. And third case, I think I'm gonna not write anymore. Third case is when you have a plane. So when you have a plane and parallel, let's say to xy, okay, xy plane, or a plane parallel to xz, or plane parallel to the yz. So that's a very simple case, right? Yeah. So those three are sort of a very special case here, not very general. Okay. Yeah. So that's the three cases that we have gone over in the last lecture. So now today we're going to finish the last case, and this is the case when you have a more general case that is here. Okay. So this is a case when you have a regular surface. Okay. Z equal to f of x, y. Okay. So this is a surface, right? And this kind of surface, if you recall that, we call this kind of surface explicit. Okay, explicit surface. So why is it explicit? Because we have exactly the expression for z equal to something, right? That's explicit. Okay. So in this particular case, then how do we do this surface integral here? Okay, yeah. Just bear in mind that this case number 4 basically includes this case number 3, right? Yeah. Okay, so when you have this kind of surface here, so the surface basically, let's rewrite this surface into this format. Okay, so z minus fxy equal to 0, right? Yeah. And surface integral, you only need two variables. So you have x, y, z. So we need to pick two out of here, right? So generally, what we pick is we're going to pick x and y basically as the variables for the integral. Okay. Yeah. For the integration. So if I pick this one here, okay, and I'll write the results at here, and then I'll roughly show you where it is from here. Okay. So if you look at your original surface integral definition, what we need is we need this n hat dA, right? We need this guy here. So if you look at this original formula, you have f dot this n hat dA. So f is a vector field that's given. And what we need is given this, you need this one. We want to figure this out, and then we can do the integral, right? Yeah. So this n hat dA, well, we're going to be able to find this actually equal to this. Okay. So we'll be able to find this n hat dA is this guy here. Now, if I look at what's inside here, okay? What's inside here? So this is actually what? If I define this portion and here as a w, okay? So if you define your w equal to z minus f x y, okay? So this is a function of three variables, right? Yeah. Then what does del w give us again? Give us this Actually, what does del W? What is it called? First of all, del W is called gradient. What's the meaning of the gradient? Outward, not necessarily outward, but it's a vector pointing yes, that's right. This is a vector normal to the surface, right, of this z equal to fxy. Okay, so this del W here, actually if you calculate del W, here's a W. Here, if you calculate del W, what would that be? This is what you get, right? Yeah. So del W, we know that this guy is perpendicular to the surface. Okay, z equal to fxy. Okay, yeah. Okay, so I don't want to confuse it here, but back to this these results, which I'm going to show you. But back to the results here. Okay, n hat dA equal to this. I have a positive and negative here, basically meaning the n hat can be two directions, right? Yeah. Which direction we choose? That's basically based on the actual question. Usually, okay, we're going to choose the so-called upward direction. Basically, we choose this positive one here. Okay, positive. Yeah. Now, del W is this. So this portion is del W. But you need to be careful. Is the del W is not n hat. Okay, the del W is not n hat. But what is n hat? N hat is del W over del W. Okay, that's n hat. All right? Yeah. So if I do this one here, let's see, Let's see what do I get? What do I get here? Del W over del W is negative fx here, negative sy here, and then over the root or the magnitude of this. So the magnitude is fx squared, fy squared plus 1, right? That's the magnitude. Okay? Yeah. Now this is n hat. Okay? So n hat is unit normal vectors, which comes from the del W that's perpendicular to the surface. Okay? So then naturally, okay, let's go back here. This is n hat dA equal to this. This is n hat. Now, can you tell me what's dA now? If this is n hat, this is n hat dA, then dA must be what? So you have this equal to this, very simple. So just substitute this n hat over here, right? Yeah. Magnitude dx, not the magnitude. It's a 1 over the magnitude, right? What's going on here? The pen's not working. Second. Okay. So the dA is 1 over this, right? Is that right? See, if you multiply this n hat with the dA, multiply this with this, so this cancel this out, and you only have this left, and then you have this dxy there, right? Yeah. Can you see this?
Wouldn't that give you 1 over fx squared?
Oh, sorry. What's going on here? Yes, of course. Yeah. My bad. Yeah. Okay. Yeah. So that's dA. Now remember, what's the dA? dA represents the area, the magnitude of that small area. Basically, how big is the small patch there, right? Yeah. So as a matter of fact, on the sideline here, okay, on the sideline here, if the question becomes this one here, this is a regular surface, z equal to fxy. And can you calculate the total surface area? Right? Can you calculate the total surface area? So what would you do? You pick one small area and you add all the small area up, right? That's the total surface area. So if I use integral, basically the total surface area will equal to, which is what? The dA here, right? The dA. Okay? So basically it's this integral. Okay, so this is integral. Yeah. Yeah, the computer has given me in trouble. Hopefully it can last until the last day of this term here. Okay. Yeah. So, okay, now I'm kind of jumping here because I didn't show you anything where this is from here, right? Basically, I'm kind of teaching you from this level here and telling you what this is, right? So the only question is, where is this from? How would you derive this formula here, right? So here's a roughly idea of how would you derive that thing, okay? And we're talking about the surface integral, so let's get ourselves a surface here. Okay. So let's suppose I have a surface set here, okay, and this is z equal to fxy, okay, yeah. And then, okay, what we do is we're gonna pick a small patch, okay, on the surface. Okay, so let's say I'm gonna pick a rectangle right here, okay. Not necessarily rectangle. Let's say just pick a parallelogram type of a small patch right here, okay, yeah. And then maybe what I pick here is the way I pick is this. If I project that onto the xy plane, I would get, okay, a small patch too. Okay, so I would get a small patch like this right here, right? Yeah. So let's say this corner, okay, this corner of this rectangle here, okay, is xy, okay, is xy here. Because it's very small, okay, very small. So which means when I go from here to here, there's a small increase of delta x, because this is x-axis, so y is not changing. There's a small increase of delta x. So this side, the coordinate is x plus delta x, y. Okay? And then for this side of the delta, for this side of coordinates here, it's the increase in the y direction. So it's y plus delta y. Alright? Yeah. So basically, this little guy here has a delta x and delta y, okay, on both sides of this length. Okay. Then going upward here, okay, going upward, for this coordinate xy, basically giving a point xy, and at this point the height, right, the height can be obtained z equal to fxy here, right? Yeah. Now, what will be the coordinates of this point then? For the coordinate of this point here, right, it will be what? It will be x, y, and then f of x, y, right? So that's this point, the coordinates of that point. Similarly, you can get coordinate for this point and coordinates for this point. So the coordinates for this point will be x plus delta x, y, and f, x plus delta x, okay, y, like this. So basically plugging x plus delta x and y into this surface, and you got the z components right here. And this side here, okay, is going to be x, y plus delta y, f of x, y plus delta y. Right? So that's that coordinate. Right? Yeah. So Given a small rectangle at here in the xy plane, you have a corresponding, okay, sort of a parallelogram, okay, on the surface S. All right. So now what we're going to do is I'm going to create two vectors. One vector from here to here, another vector from here to here, right? Yeah. So let's call this is a vector u, this is a vector v. Okay. So for this parallelogram, so it's like this, right? For this parallelogram, this is u and this is v. Okay, that's the parallelogram. Now, how do we obtain the u and v? Well, how do I put? Because I already have the coordinates here, right? So for the u, which is going to be basically this coordinates minus this coordinates. So that's going to be the u, right? For the v, it's going to be this coordinates minus this coordinates. That make sense? Yeah. So that's how you obtain the u here, okay? So which is, I'm not writing the u and the v anymore. So the u, v, okay, are from corner, okay, coordinates. Okay, so that's u and v. Now, if you recall in the first lecture of this course, how do I obtain the area of this parallelogram? Actually, not the first, second one. Dot product, cross product. Cross product. Yeah. So the area of this parallelogram, the area equal to the absolute value u cross v, right? That's the area. So what we're looking for, remember what we're looking for, huh? This is a small patch of area. What we're looking for is actually not just the magnitude of the area, but also including the direction. So we're looking for actually is there's n hat here. There's an n hat dA, right? So for any area on the surface, there's always an orientation. And orientation is indicated by the n hat. So what we need is n hat, not n vector, n hat dA, right? N hat dA. Now, here is the parallelogram, and you know that the area is given by u hat v, which is basically the magnitude. If I want this n hat, then the n hat must be given by what? By the cross product, by the direction of the cross product here, right? Yeah. So that basically what that tells me is this u hat cross v, okay, essentially give me this n hat dA, right? dA is the magnitude, n hat is the direction. That's it, right? So all you need to do is, the key step is here. Use this coordinate, subtract that coordinate. Use this coordinate, subtract that coordinate, got to the two vector, and then you do the cross product, and you get n hat dA. So that's what happened in my lecture notes there. I did the calculation, and you calculate this one here. That's what we got at this, where is it? At here. Okay, that's the result how we get here. Okay, yeah. So okay, you got this. Okay. Now, if you flip the direction v and u, then you got basically the negative sign there. Okay, yeah, the negative. Okay, so what I require you, okay, not that you derive this one, but what I require you, of course, you have the formula sheet. You need to understand what this n hat dA is. You also need to understand what n hat is, what dA is, because in the past I've seen the mistake is people treat this term as n hat, okay, but that's not n hat. Okay, yeah. Okay, so now I'm ready to do some examples that are here, right? Yeah, to do some examples. So I have a vector field, which is this. Okay. And let's say my surface is z equal to x squared plus y squared, and z is between 0 and 1. Okay. And I want to have the surface integral or the flux, okay, across this surface. Okay? Across the surface here. Okay, so when you have such an example, such a question in here, okay, when you have such a question here, so usually the question number one is number one is looking for is what's the orientation of the surface? Is it given in the question or not? So for now, actually the question didn't tell you the orientation yet, right? Because whenever you have a surface, you always have two directions, right? When you have a closed surface, it can pointing outward or pointing inward. When you have the regular surface, can be up or can be down. Okay. So let's see in this question here, I'm going to say the S is oriented up here. Okay, that's oriented up. So when this information is given, what actually next you should think about is, and that basically tells you what shall we take about the n hat d or n hat dA, right? So you always have two basically positive or negative for n hat dA. One's positive and negative, right? So when you see oriented up, so you basically for this particular case you're looking at is going to be this guy here, right? Okay. So because in this particular case the one is positive, so you always have a positive component for the n hat. Okay, so before we do the calculation in here, so let's draw this surface out. So this is a surface at here, 0 to 1. So it's a paraboloid between 0 and 1 for the z component. And F is a vector field. Okay? If I draw the F vector out, so it's z k hat. So at xy plane, it's 0. And as z is started to increase, then the magnitude start to increase. Right? So that's basically the F vector field. Okay. So now let me ask a question. What do you think the results of this flux here? Do you think it's going to be a positive, negative, or 0, or you don't know? It's positive, right? Because I said it's oriented up, so that's why you said it's positive, right? But if I said S is oriented down, then the flux actually is going to be a negative quantity. Okay? So it's going to be a positive. Let's calculate this one using this what we just learned over there, right? Okay, so n hat dA in first for n hat dA. Okay, so dA equal to n hat dA. Okay, and according to my formula, it's negative fx, negative fy, 1 dx dy. Okay, so for our surface, it's z equal to this. So basically, what we have is z minus x squared minus y squared equal to 0. Okay, so this quantity here, okay, is what we're going to do here. So what is f here? F is this, right? This is z minus f of x y here. Okay, so this is f here. Okay, this is f. So in other words, f of x y equal to x squared plus y squared in this question. Okay. Okay, so now let's calculate this vector here. Negative partial f over partial x, which is negative 2x. Negative partial f over partial y. Okay. So that's what we get. So once you get this portion out, you pretty much solve the question. Then plug this one back into the surface integral here and start to do the dot product. Okay, so let's do it. Okay, so dot product, what's f? F is 0, 0, z. Dot negative 2x, negative 2y, 1 dx dy. Okay, so dot product equal 0, 0 is gone, so there's only z components left, dx dy. Okay, yeah. Okay, so when you get to here, okay, no panic, because you will say, oh look, I got a mix of the x and y, z, right? How do I do this double integral? Remember what the z is? Z is the function here. So you're integrating over this surface here. So replace the z with your original surface. Okay. Because I've seen in the past, a lot of people, they're okay, but then up to here, and they don't know what to do with the z now, right? Okay. So up to this stage, because everything in terms of the x, y now, right? All you need to do is find the limits for the x and the y now. So how do we find the limits of x, y? It's basically back to the fundamentals of a double integral. The x and the y are based on the shadow of this surface in the xy plane. Okay, so now you have this shadow here. So the shadow will be, I guess the shadow will be what? Will be a circle, right? This will be a circle. Because the z goes from 0 to 1, so it's basically the shadow of the top ring here. And that circle is, okay, is this guy. Okay, yeah. So your x and y, okay, should be, so the limits for the x and y should be based on that circle. Well, because it's a circle, then I guess I would not prefer to use Cartesian. I would prefer to use what? Cylindrical, no?
Polar?
Polar, that's right, right? Because it's double integral, so you would prefer to use a polar. So if you use a polar right here, this x squared plus y squared becomes r squared. And dx dy becomes not r, becomes r dr and d theta, right? R dr d theta. And r goes from 0 to 1, theta goes from 0 to 2 pi. Okay, so regular stuff. Yeah, see, just from this one simple example, the surface integral, how many knowledge point have you used? Basically, from the beginning up to here, everything, right? Partial derivative, dot product, double integrals, right? Polar coordinates, so many things. Okay, so this is an easy one here. You do that as equal to pi over 2. Okay, yeah. Okay, so this is surface integral. Okay, yeah. Any questions? So there can be any other basically different situations, but really I don't see any variations. All you need to is keep in mind what is f of x, right? And how do you calculate this n hat dA? Okay, and then dot product. Okay, based on the shadow, find the limits. Okay, that's it. Any questions? All good? Yeah. Oh, by the way, I booked December 2nd. I'll send an email. I booked December 2nd, 9 o'clock or 9:30. I don't remember now. To 12 o'clock. Hopefully, your guests are going to be free by that time. Are you free at that time? No. Yeah. Yeah. So there's no class though, eh? I just want to have a sort of exam jam things before the final exam. Yeah. It's not going to be a formal lecture because 248, the final exam is right on the December 5th. And you have another one on December 4th, so I don't think the 3rd is good, so the 2nd is the only choice I have. And so what happens is probably we'll just have a either review or question and answer kind of a session there. All right? Yeah. So it's not mandatory. If you wanted to come, just come and then you can study here yourself. Otherwise, up to you. Okay. Okay. So I'll skip one example of the surface integral here. Okay. And in my lecture notes, I also included 2 more cases in terms of surface integral, and the other case is the so-called implicit surface. So, but basically, implicit surface when z cannot be expressed in terms of fxy. For example, when you have x squared plus y squared plus z squared equal to 1, that's implicit, right? That's implicit, right? So then, for that particular case, okay, what would you do to take a look at it? So we're not going to test that in the exam anymore, but I did include it in the formula sheet. And there's one more case, which is basically parameterize the surface just like a parameterize a curve. So take a look at the lecture notes, okay? Yeah. Okay, so now what I want to talk about next is the two important theorems. One is the Divergence Theorem, and the other is the Stokes Theorem. Okay. Okay, Divergence Theorem and Stokes Theorem. Now let me write down this. Let me write down the theorem first, right? And then we'll explain it a little bit. Now, first for Divergence Theorem, basically it's a 3D, okay, an analogy, okay, to the Green's theorem. Okay, to the Green theorem. Okay. So let me write down the theorem first, okay? If surface S, okay, is a closed surface, this is very important. Divergence theorem applies only to the closed surface. Okay, it's a closed surface. So because it's a closed surface, then the surface S must be bounding a region D. Okay, it must be bounding a region D. And the other important thing is, okay, the surface S, okay, we're going to have to choose our so-called oriented surface S pointing outward. So okay, pointing outward. So that's the orientation, right? Yeah. Okay, so make sure two things. Okay, one is the surface needs to be closed. Second of all, it's pointing outward, right? So that's the two key things about the divergence. If a surface is not closed, don't use divergence theorem. Okay, if you're talking about inward here, then it's actually the result is going to be the negative of the result of the divergence theorem, right? Yeah. But when you calculate the divergence theorem, remember when you use, if you use that, you actually use an outward direction for the surface. Okay? Yeah. So then, let's say now we have a vector field. So this is a couple of vector field here. F equal to M and P, okay, 3D. Okay. And the other thing is that a vector field needs to be differentiable, okay, in the region D. Okay. So essentially, it basically it needs to be continuous. For example, if the region D contains origin, and then it happened that maybe F vector field is 1 over x squared plus y squared. Maybe another one is x over x squared plus y squared. That kind of vector field, right? And then because then if you plug origin over here, then it becomes infinite here. So then you won't be able to differentiate at the origin, right? Yeah. So in that particular case, you won't be able to apply the divergence theorem here. So okay. So that's what we mean by differentiable in the region D. Okay. Okay, so that's all the necessary data here. Then here is the conclusion in here. Then what we have here is, okay, because surface is closed, so I use this double integral with the circle there, and F, okay, dA here. Right. So first is what's this? This is a surface integral, right? And surface integral gives us the flux across the surface. Okay. Now this one equal to a triple integral. So it's a triple integral over the region D enclosed by the surface S. And what do we integrate? We integrate that divergence, okay, of this vector field. Okay, so that's the divergence theorem. Okay. So divergence of the vector field, sometimes we also write it as the del dot F. Okay? Yeah. So that's divergence theorem. So you look at this theorem basically it's actually not bad. Okay, you have a surface integral, right? And the other side, okay, is basically triple integral. And what are we integrating? So just simply look at the mathematics. You're integrating del dot F over the D. So if F is given, then del dot F can be easily calculated, right? Then what's giving it here? That's basically a typical triple integral, right? If V is a spherical region, then you use spherical coordinate. If V is a cylindrical region, you use cylindrical coordinate. If V is something else, you use something else, right? Yeah. So just based on this divergence theorem, right? What it tells you basically, maybe I don't need to calculate this surface integral, and I can calculate the double integral. Sorry, I can calculate the triple integral over here to get the same results as this surface integral. Is that clear? Okay. Yeah, it's not bad, right? So the more important thing, I think, is for you to understand a little bit as to what exactly this theorem here. Now, we know that, okay, this quantity here is giving the flux. Because the divergence theorem specifically says surface S pointing outward. So basically, then this guy here, what does it give us? Give a outward flux, right? It's going to give us outward flux, okay? Yeah. And the second of all, looking at the other side here, the divergence, okay? Divergence here. Well, this is essentially, what do we integrate? We're basically integrating a divergence set here. So maybe I can just call it, it's a divergence integral. Okay, it's a divergence integral here, right? Yeah. Now, if you remember, what's the physical meaning of a del dot, or what's the physical meaning of a divergence? What does divergence of a vector field give us? Anybody? No? Divergence, basically, when you take the divergence of vector field at a certain point, right, you get either positive or either a negative value. Is that correct? So what the positive or negative value basically tell us is whether that's a sink or whether that's a source. If it's a source, basically it's a positive, it's giving out things, right? If it's a negative, basically there's things going into that point. That's what divergence basically, right? Yeah. So divergence essentially it's a flux, right, density, okay? Or sometimes some people also explain it in this way. Would you have expansion at that point, or would you have a compression at that point? Okay? Yeah. So that's what divergence basically means right here, right? Now divergence. So del dot F, okay, give us this kind of a source or sink, okay, or expansion or compression, okay, at a certain point. In vector field F, okay, in vector field F. Yeah. So that's the point, right? That's the point here. But then what we're doing is we're integrating. Basically, you're adding, right? You're adding adding this point, that point, that point, that point, the information at this point, right? Adding everything within the region D. That's what integration does. So the integration it's a total sum of the source or sink, or it's a total sum of expansion or compression. So in the end, so what this quantity tell us basically is it going to be the net effect? Is it going to be a source or sink for this region D? Is it going to be a compression or expansion, okay, for this region D? Okay. So basically, is there things out of the region D, or is there things going into the region D, right? The net effect. Okay, so that's what this triple integral does at here. Okay, yeah. So our flux, essentially, the flux across the surface S equal to the net expansion or compression inside the region D. Yeah, so that's what this equation here means, right? So, for example, right, let me give you an analogy here. Let's say you're pumping air into the tire, okay? So basically, pumping air into the tire, the action is sort of you have a constant flow into the tire here, right? Yeah. So let's say the tire is a container, the surface of the tire is a closed surface, okay? Yeah. So if you're required to calculate what's the flux, okay? What's the flux outward of the tire? Okay, what's the flux outward of the tire? What would you expect? Would you expect it's going to be a positive or negative? Because you're pumping air into it. Positive? It's going to be a negative. So, well, you think of this way here. Because you're pumping tire into it, so the air, okay, the inside of the tire, the container, the size is not going to change. Consider, okay? So when you more air into it, then what happens to the air? The air will be compressed, right? Air will be compressed. So inside it, there's this effect of the compression there, right? So that's why here you have an effect of compression. And this flux here, this divergence theorem tells us that the positive is our direction, right? It's our direction. That's why you're going to expect to have a negative, okay, flux across the tire surface, right? Yeah. If the other way around, let's say you put a tire under the sun, right? And the tire the volume is not going to change, but then the temperature change, the air is trying to expand, right? So let's say, I mean, there got to be some leak there, otherwise the tire will explode. So then the air, right, cannot be contained all the time in the tire, so it's going to be leaking out of it, right? So that's like flux out of this the tire surface, right? So you would expect a positive flux out of here, right? And similarly, you would expect to have a total effect will be an expansion or a source after this integral right here. Okay? Yeah. So that's what this divergence theorem is. Okay? Yeah. So let's see an example here. Okay? Yeah. Our application divergence theorem is very simple, okay? But sometimes very useful. Let's say this is a vector field here. X, y, I hat plus y, z, g hat plus x, z, k hat. So here's a vector field. And I wanted to calculate the flux, okay, out of a box. Okay, so the box is here. So here's a box, and we're interested in what's the flux, our flux, okay, through this surface of the cube. Okay, so surface cube. Okay, before you think about divergence theorem here, okay, let's just think of it purely, think of it based on the surface integral. So what's a surface integral? Surface integral is, or flux is S, F, N hat, dA, right? That's a surface integral, okay? Now we're talking about our flux through this cube right here, okay? So then, so we're looking at basically a flux through how many surfaces? 6. So essentially, if you really want to calculate that way, you're going to have to calculate it S1, S2, up to S6, right? S6. Okay? Yeah. Now, each one of the surface, you look at each one of the surface here. It's actually which case that we have been talking about. It's the case number, what? Case number 3, right? Number 3. So each one of the surfaces is a plane parallel to either xy or xz or yz, right? Yeah. So you can use that special case to calculate each one of them. Okay, each one of them. Okay. So let's say, for example, right? Let's see, I'm gonna calculate the flux, okay, out of this bottom surface here. Okay, out of the bottom surface. So what n hat would you choose? So let's say this is S1 here. So for the S1, what's the n hat? Negative k, exactly. Okay, that's how you pick this guy here, right? And then what's the dA over there? That's dx dy, right? Dx dy. Okay. So similarly for the other ones, you figure out your n hat and your dA. Okay. Or maybe let's try another one here. What's this side here? How about this side? For S, this is S2. Let's see. Negative what? Negative y? No, not negative y. Negative what? J hat. That's right. And dA will be? That's right. Okay? Yeah. So now you see, this is how you calculate, basically, if you calculate separately all the 6 surfaces here, right? Or 6 surfaces. Okay? Yeah. Any questions? Yeah? Okay. Okay, so as you can see, it's not that bad actually, right? But now we learn divergence theorem. So divergence theorem says if it's a closed surface, and if the vector field is differentiable in the region D enclosed by the surface S, then I can use this triple integral. So now let's take a look at the situation here. This is a vector field here. For every point inside this cube, okay, it's continuous, right? There's no infinite things. So it must be differentiable. So then I can use divergence theorem. Okay? So then that surface integral can be converted into a triple integral now. So I'm going to use this closed sign here because it's closed. Okay, it's D and then del dot F and dV. Okay, so that's what we're going to calculate. We're going to use this guy to calculate this guy, right? Yeah. So first thing is del dot F. Okay, del dot F. And del dot F is partial m over partial x, partial n over partial y, okay, partial p over partial z. Okay, so for this question here, your m is xy, your n is yz, your p is xz. So what would that give us? Y, z, x. So that gives us this guy, right? That gives this. Alright, so now I'm going to plug in this quantity into this formula. So we end up with, okay, triple integral, okay, x plus y plus z, and dv. And dv, okay, so this is a purely Cartesian thing. So I don't think that you're going to choose Cartesian other than that, okay? So spherical won't work. Okay, so we choose, okay, basically Cartesian coordinates, dx, dy, dz. Okay, so it doesn't matter the order. You can choose any orders you want. Okay, but this is a very neat cube. So the coordinates for x, y, z, they're all going from 0 to 1. Okay. Yeah. So the integral itself is not that complicated either. In the end, you got 3 over 2. Okay, 3 over 2. So it's a positive flux out of this box here. Okay, out of this box. So that's divergence theorem. Okay, yeah. To emphasize the divergence theorem, okay, First of all, it's closed. Second of all, when you calculate divergence theorem, what you're getting is outward. Okay, it's outward there. Okay, so that's what you need to be careful. Okay. Yeah. So any questions? All good? Yeah. When you learn electromagnetic fields, okay, there's a very important theorem called Gauss Theorem. Basically, actually, divergence theorem comes from the Gauss Theorem. Okay, the Gauss Theorem basically says, okay, when you have an electric field, okay, let's say it's point charge or anything, okay, then you're interested in what's the flux out of the closed surface S. Then it's equal to the total charge, okay. Okay, it's equal to the total charge, okay, or this is basically the flux, okay. Okay, this flux here. Okay. And this phi here equal to the total charge Q over epsilon naught. Epsilon naught is the electric constant. Okay, so that's Gauss theorem. So as a matter of fact, if you apply divergence theorem over here, okay, apply divergence theorem because this is a closed surface, and then it's going to be a triple integral, okay, over a region D, okay, and del dot E and dV, right? dV here. So that's divergence theorem. Okay, yeah. So this del dot E here, this del dot E, okay, essentially you can write it as rho over epsilon. The rho is called electric charge density. Okay, electric charge density. Okay. So electric charge density integrating over this whole region D, you get the capital Q. Okay, capital Q there. Okay. So those are Gauss law. Okay. Regarding the theoretical proof of this divergence theorem, check out the lecture notes or textbook. Okay, so I have a pretty lengthy of a proof there in terms of this one here. But I think if you can remember, okay, not just the formula, but also what I just said here, okay, you have an outward flux that equal to the total expansion or net compression or net source and net sink inside this region D, close by the surface S. Okay. Yeah. Okay. So last theorem, Stokes theorem. Okay, Stokes theorem. Okay, Stokes theorem is the idea of the Stokes theorem is basically it's a specialized Green theorem here. Okay, specialized Green theorem. So if you remember, what does Green theorem do? Green theorem basically it converts a line integral into a double integral. Right? That's Green theorem. Okay. However, the problem with the Green theorem is it's only applicable for a planar case. So when your curve C is in xy plane, so that's good, right? So then we can use the Green theorem here. So then the only thing is, what happens if you have a curve C, okay, in the 3D space, all right? So then what would you do, right? So let's see if I have a curve C in the 3D space at here, okay, and I'm interested in the calculation of the surface integral, the line integral, okay, the line integral over this curve C, right? Now, if it's a planar, then you can convert that into a Green theorem, double integral, okay. But in 3D, then we have to use this so-called Stokes theorem, okay, the Stokes theorem. Okay. So let me write down the theorem first, okay, and then we'll explain a little better here. let S be a smooth surface, bounded by a simple or smooth curve C. Then this line integral will equal to this guy here. Will equal to this. So this is basically the Stokes Theorem. Now I'll try to explain this Stokes Theorem here, right? Yeah. Now, first of all, if you look at this formula here, let's see what we don't know here, right? We actually know everything now, right? Do I know this cross product? Yes, I do, right? Do I know dot product? Yes, I do, right? And have we learned the surface integral? Yes. So basically, we can evaluate this side here, no problem at all, right? Yeah. But the only thing is, let's understand what happens here. As a matter of fact, we're hiring a new faculty here, and one of the topic that we want them to present is to present how do you teach Stokes Theorem. So he's coming in December. So if you are free, you can come and see if he's doing a better job than I am. So first of all, let's take a look at this here. What's del cross F? What do we call del cross F? Huh? Curl, right? Yeah. It's curl. Second of all, what does curl tell us? Curl of a certain vector field. What does it tell us? Circulation or rotation. Good? Yeah. So this is a curl F. Tell us it's a circulation, right? It's a maximum amount of circulation. Now, if I let's go back to the Green theorem for the time being, for temporary, Go back to the Green theorem. For Green theorem, here's a formula. This is the Green theorem, right? This is the Green theorem. So if I draw something out here, and basically what we're talking about here, we're talking about a closed curve C, closed curve C in the xy plane, in xy plane. And then the line integral basically equal to this one here. Now let's examine this a little bit here. Del cross F, right? Del cross F talks about is circulation. So now what we're saying is, if I look at a very, very small area over here, what will be the circulation around that point? And what will be the circulation around this point? And what will be the circulation around this point here, right? Yeah. So basically, you look at inside this curve C, at each small location, there's maybe a circulation, maybe not, right? Yeah. And how do I get that small quantity there? How do I get the small quantity of also the circulation around the area? How do you get? You do this step here. So this guy at this location here, if I call it microscopic circulation, that basically equal to the curl F dot K hat. Now recall the circulation. Circulation has two basically concepts. One is the direction. The other is the basically direction is determined by the area that you picked here. So in this particular case, the direction must be, because you use your right hand rule, the direction must be pointing up, right? Must be pointing up. So that's why you use the curl dot K hat. So you're looking for the microscopic circulation in the k hat direction. So that's why I use curl F dot the k hat. Okay, that's the circulation. This is the microscopic circulation at different locations at here. Okay, and then there comes this integral. So you're adding all the microscopic circulation within the region R. So then that becomes the so-called macroscopic circulation, right? And this macroscopic circulation is indicated by which one? By the circulation around this curve C. Okay? See, that's the idea of this Green theorem right here, right? Yeah, Green theorem. Okay. So now, if I go back to 3D at a case, 3D case right here, 3D, right? So 3D case meaning 3D case meaning we have in 3D, okay, we have a surface. Okay. Excuse me. So let's say I'm going to draw a curve here, but it's just to be here. So maybe the curve is this, okay, and maybe the surface is this. Okay. So curve C is over here. Okay, curve C is here. Okay. There's one important thing I haven't mentioned yet. Okay, I need to talk to you after this one here. Okay, so one important thing is the surface S and curve C needs to be oriented compatibly. Okay, just remember what I just said here. Okay, but let's finish this microscopic circulation first, and then we'll get on to the compatibility of the orientation. Right? Yeah. Okay. So now here's the surface S right here. Okay, here's surface S. If I think about the same idea, right? What will be the microscopic circulation around the surface S? So let's say here is a small area here. Okay, so then there's a small amount of microscopic circulation around here, and maybe over here it's going to be over here, right? It's here. So maybe here it's going to be over here. Okay. So if I draw a small circle or a circle parallel to the surface at there, okay. Now basically the direction of the circulation is indicated by. Actually, I draw the wrong direction. The other direction. Okay. Let's say this is the direction we're talking about here. Okay, this is the direction. Okay, because my C is draw the other direction. Yes, that's right. Okay. So for this particular one here, the microscopic circulation, okay, that will equal to the curl F. So it's not going to dot k hat anymore, right? So we need the circulation at that location in which direction? So for this guy here, what would be the direction representing that little patch over here? Come again? A what? N hat, exactly. So at that location, it's going to be the n hat representing the direction. So it's going to be dot this n hat, right? Excellent. Okay? Yeah. So that's the microscopic circulation at that location. Okay? And now you're looking for what's the total circulation, okay, or the macroscopic circulation around the S here. So what do you do? That's what we do this integral at here, right? Integral here. Okay? Yeah. And the Stokes Theorem basically tells us the total circulation around the S is the same as the circulation around this C at here. Okay? Yeah. Was that good? So that's basically the meaning of the Stokes Theorem right here. Okay? Now, then come back to the specific now. Okay? Number one is, okay, Stokes Theorem is not arbitrary here. You have to basically arrange, okay, this S and C compatibly. Okay? So I'll explain what compatible means at here. Okay? Compatible basically means, okay, you have to satisfy the right-hand rule for the orientation of S and C. Okay? So orient C and S to satisfy right-hand rule. Okay, so here's a funny exercise now for you to practice the right-hand rule. Okay, so let's see. This is what's going to happen at here, right? Yeah. So I'll give you a couple of these things here, and then we'll try to exercise it here. So here is curve C here. Okay. Here's the curve C. Here's the S bounded by the curve C. Yeah.
For this sort of picture, when the surface is, say, whatever it is, and the C is almost like a cross-section of that surface somewhere?
That's right.
Okay.
Yeah, excellent point. Now, maybe before we talk about orientation here, let's see, there's another point in here. Given a curve C, how many surfaces does the curve C will bound? How many? Giving a curve C here, how many surfaces do you think the curve C will bound? Infinite. So if I have a surface here, that's another one, right? If you are going this way here, that's another. So all these surfaces are basically all bounded by the curve C. Is that right? So in other words, if I go back to the Stokes Theorem here, if you don't want to calculate this one here, you want to calculate this one here. How many choices for the surface S you can choose? Infinite, right? Infinite here. Okay. So sometimes there's a name for this one. This is called surface independent line integral. Right. So when you do this the grading vector, we have a path independence, right? And here we have a surface independence. But anyway. Okay, so you have an infinite surface here. Okay, now let's come back to the orientation in here. Okay, orientation. Now talking about orientation, and then you should know that when we say, what do we mean by orientation of a C? It must be clockwise or counterclockwise, right? And what do we mean by orientation of the S? It must be meaning this n-hat direction. Okay, so that's basically the orientation for the two things here. Now, when we say orient them compatibly or using right-hand rule, essentially you need to orient the C direction of C and to be compatible with the n-hat. So here's right-hand rule here, right? So use your thumb, okay, pointing to the direction of the curve C. Now, curve C usually we orient it counterclockwise, looking from top. Okay, yeah. So use your thumb pointing to the direction curve C. Then use your index finger, okay, to be tangent to the surface S. Okay, to be tangent to the surface S. And then the middle finger, okay, is pointing to the n-hat direction. Okay, that's what we call it right-hand rule here. Yeah. So give a practice here. So this is C here, right? C. A thumb pointing to the direction of curve C, and your index finger tangent to the surface S. Okay, just pretend to be tangent, right? And then the middle finger, okay, pointing to the n-hat direction. Was that good? So now tell me, where should the n-hat pointing to in this case here? Upward, right? Upward. Okay. Or outward, right? Or outward. Okay. Yeah. Now the other way of there's another one here. Okay, there's another one here. So this is one way of right-hand rule here. Okay, so thumb and yeah. And anyway, so. What happens is, the other way I think is easy to draw here, right-hand rule, okay? The other way is, what you draw is, you pick a point over here, okay? Pick any point here. I'm trying to determine n-hat, right? Right-hand rule, draw this. In this particular case, we draw like this, okay? So you see this right-hand rule. So the curve your finger, the thumb point to the n-hat. And the flow of this finger direction is in the same direction of the C at here. Okay, C at here, right? So if I go over here, and it's going to be this way, Okay, right, like this, right? Yeah. So here's an analysis. So let's say now if my surface is here, if this is surface here, and this is the direction of C. Now what will be the n hat direction for the S? Right. Use either way that I teach you here to determine the n hat.
Would it be inward?
It would be inward. That's right. Right. It would be inward here. Okay. Yeah. So if you use the first choice, C pointing to the thumb pointing to the C direction, and index finger pointing tangent to the surface here. And then the middle finger is perpendicular to the S here, right? Yeah. If you use the other way there, just draw a circle at a certain point here. So that circle would be this way, right? So right hand rule, that thumb pointing into it now. Okay, you see the top one here, that's parallel to the C here. Okay, the direction of flow. Is that clear? Okay. Now you probably wonder why do we need that? Because when you calculate the surface integral, you need the n hat, right? You need n hat. Yeah, you need to have a proper n hat. So technically speaking, there is going to be a sign difference. You choose the wrong n hat, but it's actually a total concept wrong. Yeah, even if it's just a sign difference. Okay. Yeah. So here's another exercise. I think we just do the exercise. I'm going to do some example next lecture. Okay. Let's just suppose I have a cylinder. Okay. So here is a cylindrical surface. So the surface is the side of the surface is S here. Okay, it's S. Okay. Now in the next example, I give you the direction of C. And ask you the direction of orienting it to the S properly. So in this particular case, let's say my S is going to be this way. Okay, so this outward is my S direction. So then how would you orient to the C, or what would be the direction of the C for this surface here? So first of all, how many curves C bounds this surface? They're top and the bottom. There are two, right? There are two here. So here's C here. Here's C prime. Let's see. Okay. So the question is, what would be the direction of C, and what would be the direction of C prime? Yeah, try it out. So remember the n hat is outwards, right? Then if you use a first approach, your thumb should be pointing out of this cylinder here. No, thumb, the middle finger. And the thumb is always pointing to the direction of C. And the index finger is tangent to the S here. So for this particular case, this is tangent, right? This tangent here. And the thumb, the middle finger pointing out, okay? Then the thumb pointing is the direction of the C at the top, which is basically which direction? This way, right? Yeah.
I'm not understanding which way the index finger points.
Index is tangent to the surface. So if this is the surface here, tangent to the surface. So just pretend to be not, right? And right now the surface is the vertical surface on the so basically the index pointing either here or here, right? Yeah. But your middle finger pointing outwards here. Or the other way is this. You can draw a circle at here. Okay. So this top one match this, bottom one match this. Okay, circulation. Any questions? Okay. So next lecture we're going to finish up with one acute example of the Stokes Theorem, and then we'll do a quick review on the course. Okay.
entirely understand if
Yeah, just a second.